Good morning, good afternoon, good evening. Welcome to today's webinar on safety and process optimization when ashing. The webinar will be led by Tom Gould, our UK Sales Director at Verda Scientific, who will be joined by Paul Haigh, the UK Product Manager for Carbolite Gero, and Simon Rundstrom, Wretch's UK Northern General Business Manager, who will also present during the webinar. There will be a quick poll at the end of the webinar, plus there'll be a question and answer session. So please don't forget to send questions throughout the webinar using the Q&A facility in Teams. I'm Robert Pryor. I'm the Marketing Manager for Carbolite Gero and Verda Scientific UK, and I'll return at the end of the webinar for the Q&A session. Let me quickly introduce Verda Scientific and the Carbolite Gero company and the member companies of Verda Scientific. With over 1,000 employees in 22 offices around the world, Verda sets the gold standard for high-tech quality control R&D solutions in research institutions, analytical laboratories, and cutting-edge manufacturing companies. From sample preparation and particle characterization through to heat treatment, elemental analysis and hardness testing, our companies deliver significant benefits to assist your processes, your outcomes, your sustainability, and your profitability. So there are 5 companies, Carbolite Gero offering the heat treatment solutions, 2 furnace manufacturing plants here in Germany and UK. There's Wretch, milling and sieving, Ultra for elemental analysis, QATM for hardness testing and microscopy, and Microtrack MRB for particle characterization, all ably supported by a range of offices and distributors around the world. Please, after the webinar, do take the PDF slides that are available for download. Do take a look at the websites for the Carbolite Gero and Wretch products. And I hope that you'll take an opportunity to look at all of the other websites for Verda Scientific companies as we go along. And it's at that point that I'm going to now pass you over to Tom Gould, our UK Sales Manager here at Verda Scientific. So Tom, it's over to you.
Thank you, Rob, and thank you to everyone for joining today. The focus of today's webinar is on ashing techniques and safety. We've got a snapshot here of some of the industries that actually use ashing as part of their analysis work. There will be a few references to the food production and food standards, but all of the principles we're going to discuss today apply to the ashing standards that you see in all these market sectors. If you have a specific application in mind and it doesn't relate to the food standards, please contact us at the end and we'll make sure that your application aligns with the right furnace type. Rob, if you could move us on a slide, thank you.
Okay, so as Tom's just said, we're focusing on food standards, but other industries will use similar standards. So both national and international standards exist for a range of ashing applications. Those who need to ash materials may need to follow these standards, or they may have their own procedures that follow very similar methods as shown in these standards. So here we're showing a few in this table that relate to food production. In the table we can see the temperature that's required for the ashing, the time that the samples have to remain at that temperature according to these standards. And we'll discuss this later in the webinar with possible methods of reducing that time. And we also see the sample weight and the details of the crucibles to be used. So just looking a little more detail inside the standards. So in these standards, they list the apparatus that's required to carry out the ashing process. So Verda Scientific can supply, for example, the grinding mill and the electrically heated furnace and the drying oven. that is listed in this particular standard. The drying ovens used to dry the ashing dishes, so many of our standard laboratory ovens will be suitable for that. You'll see 2 ashing or incineration temperatures, maybe called ashing or incineration within these standards. So here we're seeing 550 degrees C and 900 degrees C. These are very typical temperatures for ashing processes, not just within the food industry. The temperatures have a tolerance of plus or minus 10 degrees at 550 and plus or minus 25 degrees at 900, which on the face of it, you might think are not very accurate, but you have to consider that an ashing furnace has to provide a relatively high flow of air compared with a standard conventional furnace. So pretty sensibly, the standards don't specify a particularly tight temperature uniformity tolerance. The first piece of apparatus listed, as I said, was the grinding mill, which may be required for preparing the samples before ashing. And Verda Scientific can, of course, supply this grinding mill. So I'm going to hand you over now to Simon, who's going to describe some sample preparation that may be necessary prior to ashing.
Thank you, Paul, and welcome to all. Sample preparation is crucial for getting the best possible result from the following analytical technique. Knife mills in particular have become a standard preparative tool in the food and food testing markets over the last couple of decades. Wretch offered 2 models of such knife mills, which we call a grinder mix, models GM200 and the larger, more powerful GM300. Both models are benchtop and deceptively powerful. The modus operandi for both models is the same. The motor has bipolarity, meaning it can operate in both directions. When run in the reverse direction, the blunt rear side of the knife is used for pre-grinding. This is especially useful for larger and/or harder samples. The sharp front blade is used to produce a fine and homogeneous sample that is of analytical grade fineness. As you would expect, both models have freely selectable speed settings and a very wide range of accompanying accessories in order to cater for virtually every type of foodstuff sample. You can see here online an overview table of the relevant features of each model for your perusal. Now we have prepared a short video to emphasize and illustrate these points. As you can see, it's very easy to assemble and use the instrument. The instrument has a touchscreen controller. All parameters are controlled via this touchscreen controller. So that includes the rotation speed, the direction of motion of the motor, and the time. As we talked about earlier, we often use for larger and harder samples, for instance, things like cereal bars, the blunt side of the knife first. We can use things like reduction lids to keep everything down at the bottom of the chamber, which comes into contact with the knives. Preparation times are normally very short. And as we discussed earlier, we can use the front side of the knife, which is much sharper, for getting a truly fine, homogeneous result. After the cycle has completed, you can see the results, and here are some that we prepared earlier. In summary, the grinder mix is very well suited for preparing foodstuff samples to present to a suitable ashing furnace, as we shall see. I shall hand you back over to Tom.
Thank you, Simon. Okay, so we're going to look at the ashing step next. What you will find if you go online or you look in any of the literature that we provide for this type of system, we do have selection guides that help you to identify the correct type of furnace based on the type of process that you're running. It's very important to get this right, not just from the perspective of the application to ensure that you get a good result, but also in order to protect the operator and ensure that you have a safe operation of the system. So I'm going to pass you back over to Paul momentarily just to go over some of the features that you'd see in a typical ashing furnace. Paul.
Yeah, okay, thanks, Tom. So here we can see a cross section through an ashing furnace and an image of the furnace. The QR code there would take you to the web page that shows you details of the ashing products. So at Carbolite Gero, we offer a range of furnaces with characteristics tailored to the ashing or incineration process. And we've just got listed a few key considerations for the design. So we'll start there with the airflow. So this is required for the ashing process and also from a safety perspective. Some of the test standards note that air exchange rates of up to 5 to 10 chamber volumes per minute may be required. So as we talked about earlier, that tolerance that the test standards require. So to achieve that uniformity with that level of airflow, we have preheated air. So with relatively high airflow through the chamber, it's important to preheat the incoming air to maintain the required temperature uniformity within the chamber. We also have covered heating elements. So in these processes, we definitely get off gases from the ashing process. Depending on the products being ashed, these may be aggressive. So the heating elements are protected by physical barriers. The relatively high airflow through the chamber assists in sweeping away those aggressive off gases as well. And hard wearing refractory. So this sets Carbolite Gero apart from competitors. The hard wearing refractory reduces the chances of the off gases penetrating and condensing within the insulation materials, and also provide a long life with the reduction of physical damage that might be caused by operators loading and unloading the furnace.
Thank you, Paul. So we're going to look at a video now that demonstrates the importance of the furnace selection. So we often see furnaces used in the field that are not designed for this application. So in this first shot, you can see the operators unloading the sample tray from an ashing furnace. So we actually supply these Inconel trays with the ashing furnaces, and they aid loading and unloading of the samples. And here you can see the 4 samples before they're introduced into the furnace. And then after they've been successfully ashed, this is the end result. So in the second example, we're using a general purpose chamber. So we don't have forced airflow through the chamber. We've not got a high oxygen content. And this is really the best case scenario if you're using improper furnace technology. So we don't have enough oxygen inside the chamber to essentially combust the sample. So after a period of time, the operator opens the furnace, and you can see there that the material's reignited. So best case scenario, someone unloads that sample, they leave it in there a bit longer and it takes a lot longer to ash. Worst case scenario, they remove the sample and you get an inaccurate reading. Now that's the soft outcome, but for this is what could happen if you have a high volume of volatiles in the chamber. So in this instance, we've got a build-up of volatiles. There's not an air exchange in the furnace, and we're not actually exhausting any of those off gases away from the chamber. And I think a lot of you can probably preempt what's going to happen here. But yeah, as the doors opened, we've still got 500 degrees inside the chamber. We've got an ignition source. We've got an inrush of oxygen, and the volatiles combust. So this not only poses a risk to the operator, but the furnace. Yeah, the infrastructure in the building. We could be setting fire to stuff in the surrounding area. So really, a big takeaway here: getting the right type of furnace for this application is key, not only for the process, but also for the safety of the operators.
Okay, so we'll just look in more detail at the ashing process in a graphical form. So we're showing the effect of an ashing process and the effect of burning a sample, the effect on the chamber temperature. So at the start of this graph, at time 0, we're placing a cold sample into a furnace that's already set at and already at temperature at 540 degrees C. So you'll see the red line is the furnace temperature. So you see a drop off and then you see it recovering to 540 degrees C in the first few minutes. Then it's followed by a rapid increase in temperature above the set point. So remember our set point's 540, and you see the red line rising up to 700 degrees C in this case. So that's caused by the sample material igniting, and as it burns, it's increasing the temperature in the chamber. The blue line shows the weight of the sample, and during that burning phase, we see the weight reducing. As the sample weight reduces to a constant value, we also see the temperature returning to the set point of 540 degrees C. So the rapid increase in temperature caused by the sample igniting will rapidly increase the fumes coming out of the furnace chimney as well, which could overload any fume cleaning method, such as a catalytic oxidizer or an afterburner. Placing the sample in at a much lower temperature and heating slowly by controlling the heating ramp will cause the fumes from the furnace to be spread out over a longer period and will reduce the intensity of the fumes at any one time. That may be an important safety factor for some users. So safety considerations: overloading the furnace or heating up too quickly can lead to excessive smoke, exposed flames, as we saw in the previous video, and unstable heating, so temperature spikes caused by exothermic reactions. This could also overload extraction systems, which need to be matched to the process so they can safely remove any harmful gases. So I'm going to hand over now to Tom, who's going to just talk about temperatures in the chamber.
Okay, so just taking from the information that Paul's presented to you now, and looking at how we can utilize that information to optimize the configuration of the furnace. So we've got a furnace, a diagram of a furnace on the left-hand side, and we've positioned 4 thermocouples inside the chamber for this test. We've measured the temperature in the catalyst outlet, and that's indicated by the blue dot and the blue line in the corresponding graph. We've got an orange dot that indicates the chimney outlet, so that's inside the chamber. We've got a grey dot, that's where we're measuring the sample temperature, so we're just above the load in one of the crucibles. And then we've also got the air inlet temperature, so inside the chamber. Now, what we've done is we've taken the furnace up to 540 degrees. You can see the dip in the graph that indicates where the door's been opened and the sample's been introduced. Often the furnaces are preheated for these type of tests. And then you can see the spike that follows, and specifically the spike where the grey thermocouple sitting, so above the sample. And this is showing the exothermic reaction of the sample. So the sample's taking the localized temperature up to 800 degrees over the sample. The reason this is important is if we can measure this and we can prove this, then we can also potentially reduce the operation time, so the residency time in the furnace. So this is a saving in operator time. If you're a test lab and you're running a lot of samples, we can reduce the time taken between sample runs. And there's an obvious energy saving there, which is good for the environment, but also good for the bottom line. Paul's actually going to take this a step further and show you how we can integrate this with a balance system as well.
Okay, so thanks, Tom. So Tom's just described how we might monitor the ashing process by observing the temperatures within the chamber. So an alternative method to monitor the ashing process is to observe the weight change of the sample. So we definitely call this a loss on ignition test. So we're losing mass as the sample ignites. We have the AAF BAL furnace, which has an integrated balance, which you can see in the image there on the right. Again, the QR code would take you to the web page that describes this product. As you can see, it's got an integrated balance, and also you can see in the image there's a ceramic plate at the bottom of the chamber, and that's supported on the balance via ceramic columns which are passing through holes in the insulation. So the AAF BAL allows us to capture both the temperature and the weight of the sample. We can therefore see when there's no more weight change, and therefore the ashing is complete. We have 1100 degrees C maximum temperature here, so suitable for those ashing processes we were showing earlier, 17 litre capacity, and the maximum capacity of the balance is 3 kilograms. There is an advanced option which has a communication link between the balance and the temperature controller, so both temperature and weight can be logged together. So this is a form of a basic thermogravimetric analyzer, or a TGA. We also have our sister company Ultra, who manufacture a TGA type product. So please also have a look at the Ultra website if TGA analysis is of interest to you, or just contact us and we can put you in touch with our Ultra colleagues who will know that product very well. So if we look in more detail at the graph that we were showing there, so we're investigating if we could reduce the cycle time of an ashing application. As Tom described earlier, we were looking at seeing if we could do that by monitoring the temperatures in the chamber. And here we can do this by monitoring the weight of the sample. So in the graph, what's happening is we're putting a sample into a cold furnace, and then we're setting the set point to 550 degrees C. And we can see that the ashing of the sample was complete, in fact, before the furnace even reached 550 degrees C. So the furnace heats and the sample ashes within 40 minutes. So you can see there the blue line that's falling, it's the lighter blue line that drops, and you can see that's dropping whilst the furnace temperature is around the 300 to 400 degrees C mark. The weight is shown on the right-hand scale of the graph. So that's the weight falling. And we end up with about 2% mass left in the sample. So if reducing the cycle time is critical, this could be a useful method for proving the ashing is complete in a shorter time. This allows a user to have evidence that their process is complete in that shorter period of time.
Okay, so just to look at another feature that we can offer with the furnace systems is a nice the video that just demonstrates the preheated air entering the chamber, passing over the sample, so that the high rate of oxygen exchange in the chamber encourages the combustion process, but then it's what to do with the off gases. So because we're burning at a relatively low temperature, you'll find that you get a lot of hydrocarbons, you get a lot of black smoke coming off this type of process. By incorporating either a catalytic afterburner or a pyrolytic afterburner, you can actually treat the off gases as they exit the furnace, so you're not venting to atmosphere. These products need careful deliberation, and we need to understand the thermal load, or the mass load on the afterburner. But again, if this is of interest, then we can take you through that if you give us the details of your individual application. So just a quick review of the features, the performance and the benefit of the furnace systems that we've just presented to you today. Paul, if you could take us through the features.
Yes, sure. So looking at the first column there, we have furnaces that have hard wearing insulation, so they can stand the demands of a busy testing laboratory. The heating elements are protected from chemical contamination from the samples for a long-lasting product. Then in the second column, we've got thermal insulation. The thermal insulation materials used and thermal design of the products give a cooler outer case, and the vertical lift door provides protection for the operator from heat radiation if the door is opened at high temperatures, which is often a requirement of some of these test standards. And finally, the preheated airflow through the chamber speeds up the ashing process and ensures volatiles are fully removed from the samples.
Okay, so let's look at what that actually means to the process owner or the furnace owner. Obviously, with a harder wearing insulation, we're ensuring a longer product lifetime. And again, in the times that we're in now, it's important to establish that you're purchasing products that have a long shelf life, so you can minimise your impact on the environment, but also because you'll get a longer return on investment by buying a higher quality, longer lasting product. We've also looked at lowering the risk of contamination. So with inferior insulation techniques using low thermal mass insulation, there is a risk that over time the insulation can lint and it can break away, and that can fall into your sample, obviously. With the increased insulation, we're obviously seeing a cost saving in energy usage. We're protecting the operator as well. The external surfaces in a lot of furnaces that are made with inferior technology will not give you the external surface temperatures that you need to meet to EN 61010. We've got the vertical door that keeps the hot face away from the operator, so that's another safety feature that we incorporate into the ashing furnace systems. And then also you've got the fit for purpose. I mean, we've demonstrated, I think, quite succinctly how important it is to make sure that you select the right furnace for the application in order to protect the operator. And again, that feeds into the preheated airflow, so ensuring that we've got a good airflow and oxygen exchange inside the chamber ensures faster process times, a fully ashed sample, and we're protecting the operators again. Okay, so just to summarise, I'd like to thank everyone for joining today. Carbolite Garrow have been manufacturing furnaces for 80 years, and we presented to you those 80 years of experience condensed into the product ranges that we presented to you this morning. If you do have an application in mind, please get in contact. We'll put you in touch with your local distributor in one of the 22 market units that represent the Verda Scientific group. And I'm confident if you do, you'll see reduced running costs, reduction in process time, and harder wearing equipment with a longer term benefit to the environment. So again, thank you for your time, and I'll pass you back to Rob.
Thank you very much indeed, Tom, Paul, and of course, Simon, for all of that information. I'm sure that all of us found it fascinating. Don't forget you can download the slides with the hyperlinks in there. If you've questions, keep coming with those. We'll do those in a minute. But first of all, I just wanted to put up our contact details, and what I am going to do is share a quick poll that you can answer before we turn around and look at the questions. So the poll is up there. Hopefully you can submit your answers, and I'll give you a couple of seconds to do that, and then we'll turn through to the questions that have come in. Whilst that's being answered, Tom, I'll put one of the questions to you straight away, which is about the standards have times that are set. In the standards, there are times for ashing. What about speeding up that process? A good thing, bad thing? How do you view that, please?
Yeah, so obviously the standards are often written around equipment that was established 20, 30 years ago. So definitely the duration of the ashing process is definitely erring on the side of caution. So the ashing for 3 hours, we've demonstrated already, is not necessary. I think fundamentally it comes down to what kind of industry you work in and how you can ratify reducing that ashing time. So if you're internally assessing your own product, you might take a view that actually, as long as you're happy that the weight is stabilized, why would you leave it in there for another 2 hours when it's not doing anything? Really, it's down to the people that write the standards as well to establish that you can still achieve the same result by using the right equipment. So I think it's something that needs to be looked at further, and it's a discussion to be had with not just the customers but also the people that write the industry standards.
Fantastic. Thank you very much indeed. We've had a question about whether you can get hold of a recorded version of this. Of course, there'll be a recording that's sent out to everybody afterwards. I'm going to close the poll in a few seconds. Just to mention, if anybody didn't realise, it does scroll. There is a couple of questions that may be scrolled off. So just to let you know that. And then I'm going to just come back to a question that we've had in. Tom, just bear with me whilst I manage to bring it up again. It's concerning the auto-inflammation problem that was raised, in our video. I have a person here who's trying to heat some starch material, 200 grams at 200 degrees C. After 1 day at 200 degrees C, everything was okay inside because they checked a couple of times by opening the door. But after a day, they opened the door one more time, and a few minutes later, the temperature increased and the starch started to burn. So is that really about the oxygen starvation in an incorrect furnace? Or still the volatiles, were they accumulating in that and then they've reacted, do you think? Any answers there?
I've got a few things that could be. We definitely need to understand what type of furnace are we using for a start. It could be that there was oxygen starvation, but I suspect not. If it's only a very small sample, what could be happening is that if elements are exposed in the chamber, you've got an ignition source. If the starch is very fine and they're opening and closing the door, I don't know if that present a risk, because you've got airborne particulates, which effectively would be combustible as an airborne in the right concentration. So there's that could be a consideration. But yeah, we'd need to understand exactly what type of furnace they're using to be able to give any kind of advice on that, I'd say.
I think
have them in person, and we can certainly go back to them. So thanks very much indeed for that.
Yeah, I think we should do that. I think we should have a discussion directly and properly understand how the process is set up and exactly what's happening, and then hopefully we can give some useful advice.
Brilliant. I have another question that's come in, which is, would you expect a different ash profile for samples ashed at 600 degrees C as against samples that were ashed at 500 degrees C?
Depends what's in the sample.
I think it's so it's going to be dependent on what that material is. So for sure, if something is going to be further removed as you go up between 500 and 600 degrees C, then there will be a difference. So I think it's important to either there's a test standard that's already been written and someone's predefined the temperature at which it should be burnt or incinerated, or it's something novel, and in which case then there's going to have to be tests done at those different temperatures, I think, and enough tests to build up some analysis to discover if there really is a difference. So it's going to come down to the material that's being ashed.
Cool.
You've also got chemical reactions that might take place. It's not just about when it's burning. You could have a reaction in the sample between two elements that reduces the temperature that material effectively burns. So, not to be facetious, but it's so dependent on what type of a product it is, and that's why standards exist as well. It's important to point that out, and that may influence firing times as well.
Okay, I think that's about all the questions that we have today that are directly that would be relevant for everybody. There's a couple of questions that have come in which are very specific for people, which we'll get back to you directly on. So I'd just like to take this opportunity to thank Tom to thank Simon and to thank Paul for enlightening us about safety and the process optimization of ashing. I hope that you found it useful. From the feedback I've received so far, it is useful. We will make it available as a download. The video files, the PDFs are available. When I send out an email later on today or tomorrow, you will have access to the recording and to the PDFs, and there'll be contact details for local organisations that you can contact. In the interim, if there's any information that you feel that you would like, please do come back to me directly, and you can contact us via the information that's on the screen now. So it remains to me to say, hope that we'll see you again in future at Carbon Gero and Verda Scientific webinars. And I look forward to seeing you at those webinars. But for today, thank you very much indeed. And I'm going to end this for everybody and then share the recording as soon as it's available. Thank you very much indeed, and have a great day.